Hi. In today's lecture, we move on to what's called Gauss-Jordan elimination. So in Gauss-Jordan elimination, we don't stop when the augmented matrix is in row echelon form like we did with Gaussian elimination. Instead, we require two additional things. The first is that all of the pivot elements are going to be equal to 1. And the second is that we're going to eliminate entries above the pivot elements to reach what we're going to call reduced row echelon form. So again, we begin with a system of equations and transform it into an augmented matrix. We start by locating our first pivot element. So usually we'd be starting in this northwest corner, but this element can't be 0, so we'll have to swap rows to bring a non-zero element to that pivot position. So we'll swap rows, and here I've picked row 2. You can swap with any row you'd like, row 2 or row 3. But now we have a non-zero pivot, and we want to do two things. We want to use the pivot to eliminate all of the elements below it, just like we did with Gaussian elimination. But we also want to make this pivot element equal to 1. And so the way we're going to do that is by multiplying this row by a constant. In this case, I'd multiply this entire row by -1/2, and then this element would be a 1. Now, it doesn't matter what order we perform these two tasks in. Here, we have a pretty easy elimination, since both the element that we want to eliminate and the pivot element are both equal to -2. I would just subtract these two rows. And so we'll first eliminate, and then we'll transform this element into a 1. Okay, so we're going to take the third row and subtract the first row in order to zero out this bottom element. So -2 minus -2 is 0. 5 minus 4 is 1. -4 minus -1, that's -4 plus 1, that's -3. And -2 minus 1 is -3. Okay, so we've eliminated everything below the pivot element, and now we're going to make our pivot equal to 1. And we do that just by multiplying that first row by -1/2. And now we have a 1 in that pivot position. And we have to do the same all the way across the row. Okay, so starting there, now we identify the next pivot. So that would be the next diagonal element here. Since it's already equal to 1, the only thing we have to do is use it to eliminate the entries below it. So we can do that by taking the third row and subtracting the second row. So 1 minus 1 is 0, -3 minus -1, that's -3 plus 1 is -2, and -3 minus 3 is -6. And then again, our last pivot was a 2, and we have to turn it into a 1. So we multiply the third row by -1/2. So what really differentiates Gauss-Jordan elimination is the next few steps. Here our goal is going to be to use the pivot elements to eliminate all the entries above them. So this is where we ended last time, and we have 1s in the pivot positions. And originally we started in this top left corner and made our way down to the bottom right corner. And now we're going to do the opposite. We're going to start in this bottom right corner and work our way back up. So starting in the bottom right corner, we want to eliminate the elements above this pivot. And so to do that, we can replace row 2 with row 2 plus row 3, and that will eliminate this value right here. And now, we only do this once we've already eliminated everything below the pivots, because these zeros will not affect the remainder of the calculations. So adding row 2 to row 3, we see now we get a 0 above the pivot, and then 3 plus 3 is this 6. And then we have to do the same thing with the next element above the pivot. In order to do that, I have to multiply this row by 1/2 and subtract it from this row. So row 1 minus 1/2 times row 3. So again, none of the other elements to the left of the 1/2 are going to be affected. We just start with the 1/2, subtract 1/2 to make it 0, and then we have negative 1/2 minus half of 3. So minus 1/2 minus 3/2 is minus 4/2, which is minus 2. And we're almost done. We have one more pivot with elements above it. So moving back up to our next pivot, we want to eliminate this minus 2 above it. And to do that, we're going to add 2 times the second row to the first row. So that will eliminate the element above the pivot, and 2 times 6 is 12, plus negative 2 is 10. And now we've reached what we call reduced row echelon form, where all of the pivot elements are equal to 1, and all of the elements below and above those pivot elements are equal to 0. So how does this help us? Well, let's transform back to a system of equations. We're going to have 1 times x1 equals 10. 1 times x2 equals 6. x3 equals 3. So it completely gives us our solution. It does the back substitution for us, essentially. And so the solution to the system of equations is just what's left over in this right-hand column of the augmented matrix. So to summarize, in order to perform Gauss-Jordan elimination, we take the same steps that we did in Gaussian elimination, with the added stipulation that the pivot elements should be equal to 1. If they are not, we simply multiply the row by a constant to make them equal to 1. Or we interchange rows if that's possible. We also eliminate or zero out all the elements below the pivot and all of the elements above the pivot. So we start by eliminating the ones below the pivot, and then when we're finished with that step, then we begin to eliminate all the entries above the pivots. And once we've done that, the augmented matrix is said to be in reduced row echelon form, and the process is complete. So let's try this to solve the same system of equations that we did when we practiced Gaussian elimination. If you'd like, you can pick up where you left off when you performed Gaussian elimination. And you should find the same solution you did last time. x1 equals 0, x2 equals 1, and x3 equals 2. And so that is the end of today's topic. And then next time we're going to talk about different categorizations of solutions to systems of equations.